Hello everybody, so this is part 2 of our talk on tailoring metal hydride for practical application. In this talk we will see the effect of reducing the chrysalid size on the hydrogen storage capacity, and also we will see the use of other technique to obtain a nanostructure. So first, let me talk about iron titanium alloy. This is an old and a well-known alloy. This was discovered as metal hydride in the 1970s. It could absorb temperature, hydrogen at room temperature, but the first hydrogenation, what we call activation, is very difficult. So even if the alloy could absorb hydrogen at room temperature, usually the first hydrogenation, you have to go to high temperature, like 450 degrees C in vacuum. After that, you anneal at a certain pressure, like 7 bar. You cool to room temperature, and then you go at high pressure, and you do that a couple of times. So it's a lengthy and a complicated process. So what will be ideal will be to be able to do the activation, the first hydrogenation, directly at room temperature under low pressure. So how you could do that? Well, you could substitute some element. Usually people are substituting on iron. So they replace iron by other transition element, for example, manganese. And then you could have a first hydrogenation that is quite quick, okay? But when you do that, you could change the thermodynamics and the capacity. So that's not the ideal way. Or you could add some other element, or add another alloy, and have like a nano composite. Or you could get a nanostructure. So this is what we will see in this talk. So the work that I'm showing you is the ball milling of iron titanium with some addition of zirconium. And that work was done in collaboration with Sabrina Sartori of the University of Oslo. So again, here we add 4% of zirconium to make the alloy easy to activate. We know that, but we would like to know what is the effect of ball milling. So how this compare with ball milling? So we cast the alloy by arc melting, and then we mill it on a SPEX machine, a high energy milling machine. And we mill for 5, 15, 30, and 60 minutes. And also we try cryo milling, so milling at low temperature, but this time it was in air. All this milling here was done in argon, but the milling at low temperature was done in air. And we will see that this made some problem. So this is a morphology of our powder after ball milling. So this is as cast. So we cast the sample and then we just crush it with a mortar and a pestle. And you have this big chunk of iron titanium. And then we ball mill it for 5 minutes, 15 minutes, 30 minutes, 60 minutes, and this is cryo mill. So you see that after just 5 minutes of ball milling, you have a huge reduction of particle size. But after, if you continue to mill for 15 minutes, you see that you have agglomeration of smaller particles. And this agglomeration will continue for 30 minutes and even 60 minutes. And now you see that all these particles are agglomeration of the small particle that you see here. So you don't see any small particle anymore because you have agglomeration of all of that. And for cryo-mill, you see that the particles are very small, but we think it's because it was milled in air and you have a lot of formation of oxide and it prevents agglomeration and it makes the decrypitation of the particle. So this is the X-ray diffraction pattern. So this is the as cast. You have iron titanium and also a little bit of iron 2 titanium. And when you mill, you see the peak are getting broadened because it's getting a nanocrystalline structure. But we don't have formation of any new phase. So you see the chrysalid size as cast is 23, and ball mill 5 minutes we already reduced it by a factor of 2, and it continued to be reduced. And here for 15 minutes of cryo mill we have about 15 nanometers. This is bigger than this because this milling machine is not as energetic as the specs machine, the machine that we use for milling at room temperature. So that's why this crystalline size is bigger than this one because they are taking on different machine. So this is the first hydrogenation at room temperature and under 45 bar of hydrogen. So you see this is the as cast here, and you see it activate and takes about 2 hours and a half to fully absorb hydrogen. If we cryo mill for 15 minutes, you see that the sample is totally dead. It's because we mill under in air, and then we have formation of oxide. And as we saw in part 1, in order to hydrogenate, the hydrogen has to go through the oxide layer, and here the oxide was probably too thick and it was impossible. So in the future we will do this experiment again, but under argon, and then we're confident that the sample will then absorb hydrogen. But for milling at room temperature, you see that this is 5 minutes and 15 minutes, 30 minutes, and 60 minutes. And you see that as the milling time is getting bigger, the kinetic is getting faster. So you have a faster kinetic, longer milling time give you faster kinetic, but you see that the capacity is getting down. So kinetic is getting better, but capacity is getting worse. So how could you explain that? So here we plot. So this is the hydrogen capacity as was measured as a function of milling time, and you see that the capacity is going down. And here this is the chrysalid size, again as a function of milling time, and you see the chrysalid size is also decreasing and it looks similar. So probably these two are related. So this is what we will see in the next slide. So if you consider that the chrysalid, again, from the first part, we saw that the chrysalid is the coherent domain, the crystallographic coherent domain. And so in order to break that coherency, all you need is one unit cell that is not coherent with the unit cell that is beside it. So that's more or less the thinner grain boundary you could have, is to have one unit cell that doesn't match the unit cell beside it. So for iron titanium, the unit cell is a 3 angstrom. So the we assume that the grain boundary is 0.3 nanometers. And then if we assume that the chrysalids are spherical, and of course the chrysalid that we measure by X-ray is an average, okay? But we assume that all the particles are at this average, and we assume that all of them have the same grain boundary thickness, okay? And then we could calculate the volume of that grain boundary compared to the total volume of the particle. So this is a very simple equation. So on first order, this is 3 times, that's the thickness of the grain boundary, and that's the radius of the chrysolite. Okay, so if you do that, you see that if you express the volume of the grain boundary over the total volume, these are with respect to the chrysolite size. So these are the number, and that's the capacity, the hydrogen capacity loss that we measured. And you see that these numbers are very close to these numbers. So it looks like the loss of capacity is scaling exactly as the volume, the total volume of the grain boundary. So then we could explain the loss of capacity. So when you create a new grain boundary, this acts as an hydrogen path, as we saw in the first part. So this means that it's fast kinetics because now you have more grain boundary, so you have more path for hydrogen to go into your chrysolite. But the grain boundary give a fast diffusion, but it could not store hydrogen. So hydrogen is going through the grain boundary, but doesn't stay there. So you have a loss of capacity. And of course, the more grain boundary you have, the less capacity you will have. So, and you see that for iron titanium, this scale perfectly well. But I have to tell that this loss of capacity depends on the system. So for some alloy, this loss could be minimal because when you hydrogenate, dehydrogenate, you may recreate uh, a coherency. Okay, so your chrysolite size may increase a little bit because the hydrogen will force, the unit cell that is on the grain boundary to adopt the same, to get coherent with the unit cell beside it. So this loss of capacity with the grain boundary is not true for all system, okay? But for some system, we see that it scales very well. So the other aspect that I would like to see in this talk is the other method to obtain a nanostructure. So in the field of metal hydride, we have a couple of methods that are widely used by the researcher. Maybe the one that is mainly used is equal channel angular pressing. So I will not go into detail, but here you have a piston, you have a die, and there is an angle in the die. So you take your sample, so this is your sample, and you push it through the die, so it has to go through this angle. And then by going through this angle, it will sustain a lot of strain. And so you could get a highly strained material, and also you could get nanocrystalline structure that way. The advantage is that depending on, because you could do that, you could repeat that many times, and depending on how you push back the sample, if you rotate it 90 degree or 180 degree, you could induce deformation in different plane. So this is interesting because according to the crystal structure of your material, you could say, well, I would like to induce deformation mainly in that plane and not in that other plane. So from a fundamental point of view, this is quite interesting. The disadvantage is that the bulk sample has to be filed. So after you process that, you have, so typically this dimension is maybe 1 centimeter. So you have a block of 1 centimeter by 1 centimeter by maybe a couple of centimeter long. And you have to file this block. So you more or less you modify your sample by doing that. So you induce some other deformation by just filing or by reducing in powder. And also this could be difficult to scale up. The other technique that is more and more used now is high pressure torsion. So here your sample is a thin disc that you put between two anvil, and you rotate it. You rotate the anvil and you press on it very hard. So the advantage is you have a very high strain. So maybe this is the technique that you have the highest strain. But the disadvantage is you have a very small sample. So maybe it's 1 centimeter of diameter by maybe 1 millimeter of thickness. So your sample is very, very small. And finally, we have cold rolling. So the advantage of that, it's a well-known technique, and I think it's very easy to scale because the industry is doing a lot of cold rolling. The disadvantage is usually you have to use a plate, but in our case, we solved this problem because we took the cold rolling machine and we rotated 90 degrees, so then we could process powder. Because usually our material, our metal hydride is in form of powder and not plate. So the example that I will show you today is lanthanum nickel 5. So cold rolling of lanthanum nickel 5. So we took commercial lanthanum nickel 5, we roll it in air, and after rolling, we do the first hydrogenation, the activation at 50 degree and 15 bar, and the desorption was also done at 50 degree and 5 kilopascal. And the theoretical capacity of lanthanum nickel 5 is about 1.5%. And again, I have to stress that the cold rolling was done in air. And we compare that with ball milling because ball milling is used by everybody, and everybody knows what this ball milling is doing to metal hydride. So we use a high energy mill, and the milling was done in argon, contrary to here that was done in air, and we mill for 15 and 60 minutes. So this is a morphology. So the as received one is like big block. So this is 50 micron. So this is almost 100 micron. So you have big particle. And when you cold roll, basically what you do, you take all these particles and you make a small plate with it. Okay. So you see that and then we took this plate after rolling once, we take the plate, we fold it in two, and we roll again. So after each rolling, we have a reduction of 50% of our plate. Okay, so so this is after 5, 12, and 25 roll, and you see the morphology of the plate do not change so much. But of course, we will have reduction of crystallite size and strain because we are every time after every roll we reduce the thickness of that plate by 50%. And this is ball mill 15 minutes. So you see, as we saw previously, you have agglomeration of smaller particle here, and after 60 minutes, you more or less, you take these particles and you break them again. So you see the particles are smaller and you have even smaller particle here. Okay. So this is the first hydrogenation, the activation at 50 degree and 15 bar. So this is the as received. So you see the as received. It's very difficult. It takes forever to activate. And if you ball mill 15 minutes, you see that it's very fast. The sample is taking hydrogen right away. Okay, but you have a loss of capacity here. Okay, but if you ball mill more, if you ball mill 60 minutes, you see that you have a reduction of capacity and the sample is almost dead again. It's even worse than the as cast. But if you do cold rolling, you see 5 times cold rolling. It's quite fast, not as fast as ball milling, but you see we have almost full capacity. And if we roll 12 times or 25 times, you see that 12 times actually it's getting a little bit slower. The incubation time is longer, but we have almost no loss of capacity. But if we keep cold rolling, we have a loss of capacity because again we do all of that in air. So as we roll, we will start to produce oxide and to make oxide, and then it will reduce the capacity. So this is the desorption. So you see that this is the desorption of the as received, and this is the ball mill 15 minutes. So it's quite fast, and that's the ball mill of 60 minutes. It's slow, but what is interesting is that all of them, the ball mill 15 minutes and all the cold rolling, all of them have more or less the same kinetic. They just the only difference is the capacity, but they all have the same kinetic. So the point is, after one cycle, they almost have all the same capacity, the same kinetics. And this is what you see on the second absorption. Okay, so on the second absorption, you see that all of them are absorbing at the same rate. So the difficulty is the first hydrogenation. Then you have a difference of kinetic between all of them. But after the first hydrogenation, and this is a common example for many metal hydride, after the activation, then the kinetic is the same. The only thing that is different is the capacity. So this is the diffraction pattern. So as received, cold roll 5 times, 12 times, 25, and ball mill, and you see that 15 minutes of ball mill, the peak are already quite broad compared to 5 cold roll. The peak are broader, but not so much. Okay, so ball milling is much more efficient to reduce into nano crystalline structure, and you see it here. So as synthesized, so this is as received, it's 50, this is in nanometer, so 50 nanometer, and ball milling 15 minutes, you reduce that by a factor, almost a factor of 10. So it's 6.9, and 60 minutes, you go down to 5 nanometer. While for the cold roll, you see it's 21 nanometer, and then 12, and then 9. So you have a reduction of chrysalid size, but not as important as for the ball milling. Okay. And this is after 2 cycles of hydrogenation. So you see that even for the as received, the chrysalid size will reduce in this case because of the decrypitation of your material. But you see here, you go from 21 to 16, So you have a reduction, but here you have an increase, okay? And here it's more or less constant, but it doesn't absorb hydrogen so much. But so you see that it looks like you have like a natural size of chrysolite. After cycling, it will tend to have like a certain size of chrysolite. Okay, so so the conclusion for the lanthanum nickel 5 is that cold rolling sample present a faster activation despite having similar chrysolite size than ball milling. So the point that I want to give you here is that nanocrystalline is important for kinetics and for activation, but it's not the only parameter. Okay, some other characteristic also have an effect on the hydrogenation kinetics. Okay, so cold rolling 5 times at the highest reversible capacity and the shortest incubation time of all the cold roll sample. For ball milling, if you ball mill for too long, it has a detrimental effect, so it's not good to ball mill for too long and to try to reduce the chrysolite size at a very, very small. Sometimes it's better to have a chrysolite size that is a little bit bigger, but you still have faster kinetic. Up to now, the exact reason for activation and enhancement with cold rolling is still unclear to us, but it's known that cold rolling increases the number of high-angled grain boundary. But in our case, it still has to be proved. We still have to do some experiment about that. So in conclusion of that course, I hope I show you that metal hydride are attractive material for hydrogen storage, but we need more development. We need to reduce the cost to get better capacity and also to improve the cycling. Nanocrystallinity is a good way to improve the kinetic, but it has an impact on capacity. And we saw that many techniques could be used to get a nanocrystalline structure. So with this, I will end my course. I would like to thank you for your attention, and I hope you will have a better understanding of metal hydride now. Thank you very much. Bye bye.